Hi guys, so this is transformations of graphs. So, uh, so when complex numbers uh, are on an Argand diagram, then the three things that are left hand side, when one of those things happens to it, there's some common trends that happen. So, the first one we're going to look at is when you a complex number. So let's just take a complex number first of all. Let's just take a simple one. So if we had um, 3 plus 2i, so that point what I'm drawing in there, that's 3 plus 2i. So we go across 3 and up to 2. Uh, so let's have a think. When we multiply a complex number by a real number, so when we multiply 3 plus 2i, something actually happens, and I'm going to show you now. So let's just take a nice simple real number like 2 as an example. So if I multiply 3 plus 2i by 2, we get 6 plus 4i. So 6 plus 4i, then if I was to plot that there on the Argand diagram, it would be this point here. So the thing to notice is that those 2 points are actually in a straight line from the origin. So what actually happens, and it doesn't matter what number I multiply here by, whatever real number it is, if I was to multiply it by 3, for example, I'll just go back and multiply it by 3. Then I would get 9 plus 6i. So 9 plus 6i, you can't really see it on the diagram here, but it would be 9 will be about there and 6 will be about there. So you see again that it's actually still in a straight line from the origin. So it doesn't matter what real number you multiply a complex number by, it'll actually just be on another bit from the complex number in the same direction, so the same as if you're drawing a straight line through the origin and the complex number itself. So that's just something to recognize, because you'll have to do solve problems by knowing that afterwards. Let's look at the second one here. So the second one is adding. So anyway, if you look back to the first one, so moves it further in the same direction. So that's the thing you need to remember. Second one is adding the same complex number to different complex numbers. So we've got one complex number down here, that's 3 plus 2i. Let's put down another one. So we'll go with 2 minus 4i. So that's another one. And then we'll just do one more as well. So we'll take one over here. So minus 3 minus 3i. So there's a common trend that if you add the same complex number to different complex numbers, so I'm just going to make up another complex number to add to each of these. So we'll just pick one nice and simple. We'll just do 1 plus 2i. So I'm going to add 1 plus 2i to the three of them, and then we're going to add them together. So we're going to just add. So I'm going to do it quickly, but remember, when you're adding two complex numbers together, you just add the real parts together and then you add the imaginary parts together. So that the first one added together would give us 4 plus 4i. Second one, if we add them together, we'll get 3, and then we have to do minus 4 plus 2, so that would be minus 2i. And then minus 3 plus 1 would be minus 2, and minus 3i plus 2i would be minus I. So let's just go and plot them on the diagram now then. So 4 plus 4i would be up here. 3 minus 2i would be down here, and then minus 2 minus I would be here. So hopefully it looks obvious from where you're looking, but what actually happens is, so this one here has actually moved up there like that. This one here has moved up there like that, and this one here has just moved up there like that. So what actually happens is they all move in the same direction. Alright, so it might seem kind of obvious maybe if you think about it enough that they would do that. But what happens is if you take difference, so if I took another complex number here, I know that if I add 1 plus 2i, it's just going to move it up like that, so it would end up there. Because you can see here it's kind of moving up 2 boxes and it's moving across 1 box to the right. So it doesn't matter what point you have on the graph. If I took another one down here, it would move up there like that and it would end up there. So that's the second one then. So adding the same complex number to different complex numbers, a translation happens, so they all move in the same direction. The last one is multiplying a complex number by I. Alright, so let's go back to, I think the one we had at the start was 2 plus 3i or something like that anyway. If you multiply it by I, and this works for any complex number then, so if I was to multiply that by I would get 2i plus 3i squared. But then you should remember that I squared is the same thing as minus 1. So we get 2i minus 3. And that's the same thing as minus 3 plus 2i. So let's go and plot minus 3 plus 2i on the graph. So it ends up here. So it might be a little bit awkward to see there, but what actually happens it's moved the point 90 degrees. So it's actually moved it anti-clockwise 90 degrees. So it's moved the point from there around to here. And it's actually moved it 90 degrees. And I know it might be a little bit hard to see there because I'm not using a ruler on that. But it will work for every single complex number. So it doesn't matter where you draw a complex number on the graph. It'll always move it anti-clockwise. Should be anti-clockwise there. So 90 degrees anti-clockwise. Okay, so that's the 3 of them kind of shown or explained then. So here's a couple of examples then. So the first one, given that z2 equals a multiplied by z1, find a. So let's have a look at what's going on in the graph anyway. So z1 you should be able to see is here, and then z2 is up here. So we know from the first rule that we looked at there that because multiplying a complex number by a real number, and a has to be a real number here, it just moves it further on in the same direction. So basically z1 has been multiplied by something to give us z2. So z1 has been multiplied by something to give us z2. So we have to figure out what has z1 been multiplied by to get z2. Well, z1 is it's 2 plus 2i. Okay, so you can read that off the Argand diagram. So 2 plus 2i, and it's moved on. So z2 then is 6 plus 6i. So really what you're kind of thinking about is what would 2 plus 2i have to be multiplied by to give 6 plus 6i. So you should be able to see, I mean, if you just take the real parts, 2 to 6, so what does 2 have to be multiplied to give 6? It's obviously 3. So a has to be equal 3 there. The next one, given that z3 equals z1 plus z, find z. So now we're using the middle one, the middle rule that we looked at, so that they all move in the same direction. So z3 anyway is 7 plus 3i. So that has to equal whatever z1 is. So z1 is z2 plus 2i plus z plus whatever z is. So we're not told what z is, so we have to work it out. But we know from the second rule that 7 plus 3i, which is z3, has to equal z1, which is 2 plus 2i, plus this z, whatever z is. And then what you can actually do is you can move across the 2, and when you move across the equal sign or take 2 away from both sides, we get 5 over here because 7 minus 2 was 5. And then we can take away 2i as well from 3i, so that would be plus I. And that just leaves us with z there, so it actually turned into kind of an equation. So that's using the middle rule there to find out what the complex number z was. If you want to pause the video there now and just have a look at this and have a think about it, maybe try it, and then I'll then play it on and I'll go through the answer to this one. So you're asked to show that z2 equals I z1. So you know you're going to have to multiply I by z1. So look at z1 and write down what the complex number is and multiply it by I, and it should give you then whatever z2 is. So that's how to do the first one. So if you want to pause the video now and have a go at it. Right, so z2 on the graph is here. So if we just write down what z2 is anyway, it's minus 3 plus 4i. So that has to equal I multiplied by z1, and we know that z1 is 4 plus 3i. So if I multiply out the brackets, I'm going to get 4i plus 3i squared, and that is going to be, because I squared is minus 1, we know that 4i minus 3, because we'll get a minus 1 multiplied by 3, and that's the same thing as minus 3 plus 4i, so we actually get the same thing then. So we get the same thing on both sides of the equal sign. So I've shown that z2 equals I times z1, so it's rotated it anti-clockwise by 90 degrees. Which one of the points then for second one, z3, z4 or z5 represents I z2? So we know that it's going to be rotated anti-clockwise 90 degrees. So I mean, if you're to kind of try and judge from the graph and draw 90 degrees the other way, it has to go down here, so it has to be this one really, z5. So you can kind of just write down the answer there. If you wanted to show it numerically, then we'll just do I multiplied by z2. So z2 is minus 3 plus 4i. So I multiplied by minus 3 is minus 3i. I multiplied by 4i would be plus 4i squared, and then we have to, because I squared is minus 1, really that's minus 3i minus 4, and that's the same thing as minus 4 minus 3i. So minus 4 minus 3i has to be the answer then, and obviously then on the graph that is minus 4 minus 3i, so answer there would be z5.